Earlier in this section, I told you about the value of treating the policy as a probability distribution. First, it allows us to describe the entire MDP as a set of two probabilities, one representing the environment dynamics and one representing the agent. This allows us to reason about the MDP mathematically and find a solution to both the prediction and control problems, as we just did. The other important reason, which I mentioned briefly earlier, is that in order to find the best action, we must first know the result of performing different actions. In other words, we must have collected those samples. Here is the problem. When we take the argmax overall actions, Q of SA, the Q value here is not changing that much from one episode to the next. Let's say we have 3 actions, so we want to choose from Q of SA1, Q of SA2, and Q of SA3. Well, perhaps we initialized Q of SA1 and Q of SA2 to 0, while we initialized Q of SA3 to 1. Also assume that all the rewards are positive. During the process of playing the game, maybe Q of SA3 gets updated to a value of 2. We will now always choose action 3 because that gives us the best Q value out of the 3 possible actions. The problem is we don't know the true values of Q of SA1 and Q of SA2 because we never collected data from performing those actions. How do we know the values of the other actions if we have never actually performed those actions? In fact, we don't know those values at all. We just happen to initialize them to 0. Because of that, there is no way for us to confidently choose the right action. This is a more general problem known as the explore-exploit dilemma. Suppose you go to a casino, and you're playing a simplified version of slot machines. You have several slot machines to choose from, and you don't know which one you should play. However, you do know that not all these slot machines yield the same reward. As I said, these slot machines are simplified, so there are only 2 possible outcomes. You can either win or you lose. If you win, you get $1, and if you lose, you get $0. Obviously, you would like to play the slot machine in which your chances of winning are highest. Okay, so how can you figure out which slot machine will give you the best chance of winning? Well, you cannot ask the manager of the casino because he wants to make money. He will not share that information with you. So what do? Your only method of figuring out which slot machine is best is to collect some data. So let's say you play each slot machine 1,000 times. The win rate of the slot machine is simply equal to the number of times you won divided by the total number of times you played. But what's the problem with what we just did? Let's say you have to choose between 5 slot machines. If you played each slot machine 1,000 times, that means you've played 5,000 games. Now let me remind you that playing a slot machine at a casino is not free. In general, collecting data is not free. It usually requires time, resources, or both. Let's say each time you play a slot machine, you spend 25 cents. You need to win at least 1 out of every 4 times in order to break even. Imagine that for some of these slot machines, you win 0 times. Now, it becomes clear that playing those slot machines 1,000 times would be a huge waste of both time and money. Here is another question to consider. Why should we collect 1,000 samples per slot machine? Why not 100? Why not 10? As you know, the more samples you collect, the better and more accurate your estimate becomes. Unfortunately, this also equates to more time and money spent. That's why we call this a dilemma. The explore-exploit dilemma means we are trying to balance both exploration and exploitation. We want to explore so that we can collect more data to find out which slot machine is truly the best. On the other hand, we want to exploit because we want to play what we believe is the best slot machine in order to win more often and make more money. These 2 forces always oppose each other. The typical answer to this problem in reinforcement learning is called Epsilon Greedy. This allows us to be greedy and exploit what we think will yield the highest future sum of rewards. But we have a small probability epsilon of choosing a random value so that we can explore and collect samples for our Q table to make our estimates of Q more accurate. And remember, they do need to be somewhat accurate in order for us to confidently choose the best action. Here's how we will do this in code. Instead of always performing the action specified by the policy, we will generate a random number between 0 and 1. If this random number is less than epsilon, we will choose an action at random. Otherwise, we will perform the action specified by the greedy policy, which is greedy with respect to Q given the state S.